Hello, this is Mr. White, and this video is on the change of variables technique for anti-deriving, also known as U-substitution. Here are the two exercises for this video. Okay, for this first exercise, let's discuss how this problem would be different if the plus 1 underneath the radical, let's say that plus 1 were not even there. Well, in that case, we would just distribute this root 5x, and we could really think of that root 5x as root 5 times root x, but of course root x is just x to the 1/2 power. And when we distribute that to this x, we would get root 5x to the 3/2 power. And then when we distribute it to the 2, we'd get 2 root 5 x to the 1/2. And that would be a relatively easy function to anti-derive. So all our old tricks, all the tricks we've learned up to this point would serve us well here. But let's now take a look at what the actual problem is, what the actual exercise is. And notice that the plus 1 prevents us from being able to distribute so easily. If you were to try to distribute the root 5x plus 1 to this x here, there's no longer any way to combine those x's as we did before, unless you're willing to take this x and bring it underneath the radical, which would present other problems. So enter the need for a new technique, U-substitution, or change of variables. And the general rule for U-substitution is to define U to equal whatever expression is underneath the radical or inside parentheses. So if instead of radical 5x plus 1, if you had 5x plus 1 quantity to the 7th power, you would also set U equal to the thing inside the parentheses. But back to this problem here. We'll define U equals 5x plus 1. And the idea is that we'll proceed to replace every single x that appears in the original integral. We're going to replace it with U. So not only this x here, or this entire expression, but we'll need to handle this x here, and we'll even need to handle the dx, and replace all those x's with expressions of U. Therefore, U substitution. So at this point, we've got the 5x plus 1 covered. That'll be replaced by just U. In general, I think it's a good idea to tackle the dx next. And I probably won't be backing up that claim here in this video, but we will address it in class. So as far as the dx goes, let's take the derivative of this U. D over dx, and then d over dx. And that's going to give us du over dx. And what is the derivative of 5x plus 1 with respect to x? Well, it's just 5, right? And if I just copy that down here, and if I multiply both sides by dx, that essentially brings this dx over here. And if I then divide both sides by 5, that brings the 5 over here. So what have we done? Well, again, as I mentioned earlier, this 5x plus 1 can be replaced by this u. And we now see that this dx can be replaced by du over 5. So we have one more expression to look at. We now need to tackle this. So let's take our original u definition here, and let's rearrange that. And we see that if I subtract 1 from both sides, and then divide by 5, I'll get u minus 1 divided by 5 equals x. But I'm really not interested in just getting x alone. I'm really more interested in x plus 2. So let's go ahead and add the 2 to both sides. And then on the left side, I'll add it in the form of 10 over 5. That's the same thing as 2. And I combine and get u plus 9 over 5 equals x plus 2. So we now have an expression of u that can replace this x plus 2. The puzzle pieces are in place, and we'll now use these three equations here for our substitution into the original integral. So let's do that. Integral, and instead of x plus 2, we'll do u plus 9 over 5. And instead of root 5x plus 1, we'll do root u. Or even better, u to the 1/2 power. And instead of dx, we'll do du over 5. So we've now completely u-substituted, and at first glance, this new integral may not look any more user-friendly than this old one, but it actually is. Because notice that now we can distribute the radical, the u to the 1/2. That can be distributed, whereas, as we discussed earlier, this root 5x plus 1 could not be distributed. That's what u-substitution does for us. So let's go ahead and distribute. And actually, what would probably be easier to do is let's take any constants, any annoying constants to the outside. So we've got a 5 in the denominator here and another 5 in the denominator here. That means we can bring a 1 over 25 to the outside of the integral. And on the inside of the integral, I still have the u to the 1/2, which I'll distribute to the u plus 9, and then include the du as well. So that's going to give me u to the 3/2 plus 9u to the 1/2 and du. Now that is something that we can antiderive. U to the 3/2, that's going to become u to the 5/2 with the 2/5 in front to balance it out. The u to the 1/2 here, that's going to become u to the 3/2 with a 2/3 in front to balance it out. And let's not forget the 9 in front. And since we just antiderived, I'll put the 1/25 outside some big parentheses and include the plus c. And if I just clean this up algebraically, then we get this expression. Now be careful. Sometimes students will leave this as their final answer, and you don't want to do that. You don't want your final answer to still be in terms of u. You want to go back and back substitute in that x, that 5x plus 1. So depending on the context of the problem, you do have the option of doing this at this time, in which case you would get this solution here. Again, notice that wherever I had a u, I just substituted back in the 5x plus 1. Now, there's nothing wrong with this answer. And in certain contexts, we could just put the box around it and call it done. But there are other contexts in which there might be a desire to combine these two terms. And there'll be context clues, such as if it's a multiple choice question and all your answer choices are one term instead of two. Or if you look in the back of the book of a textbook on your homework, there'll be some evidence that as to when you need to go further. So this is one possible right answer, but let's say that we are compelled to go further. Let's see how we handle that. In that case, I find it easier to not back substitute quite yet. So let's go back to the form where we just had it in terms of u, where we had our answer in terms of. And what we're going to do is we're going to factor out the greatest common factor between this term and this term. Now the fraction coefficients there make it a little bit difficult to determine what exactly is the greatest common factor, and I would generally advise to rewrite such that you have common denominators. So in this particular case, I can multiply 5 and 5 over here, and I can get 30 over 125, and I now have a common denominator. So now when I seek to take out the greatest common factor, I look at the u expressions, and I can tell the greatest common factor will include a u to the 3/2. I look at this common denominator, and I will definitely take that out. And then I look at the greatest common factor of the numerators. So I see 2 and 30. I'm going to take a 2 out. And that's my greatest common factor. So inside the big parentheses, I need to put u, because u times u to the 3/2 will give me u to the 5/2, and then my 2 over 125 covers this 2 over 125. And over here I'll put plus 15, because 2 times 15 will give me this 30, 125, 125, and then u to the 3/2 covers this u to the 3/2. We're all accounted for. So my parentheses didn't need to be that big after all. I'll keep the plus c. And now I'll back substitute in the u equals 5x plus 1. And that's going to give me 2 over 125 times 5x plus 1 to the 3/2 times, now if I put 5x plus 1 in here and then add 15, the 1 and the 15 will combine to a 16. So I'll get 5x plus 16 plus c. Now if it turned out that this coefficient here and this constant here had a common factor, I would then take that common factor and join it with the 2 over 125. In this case, obviously 5 and 16 don't have any common factors, but keep that in mind for other problems. That would be our final answer, which I'll call option number 2. And notice that now that is all one term, one big ugly term there. Now, for as much as I insist that you get in the habit of checking your anti-deriving processes by deriving, I have to admit that in the case of U-substitution, it's not always practical. It can be a long, ugly process. And you see here, I've just worked out the check for you, and you see it involves some product rule and chain rule. And it is kind of an interesting process to see how it all simplifies down back to this simple expression down at the bottom. And that does match our original integrand. So the check did work. I do suggest you do it once in a while, and we can discuss in class other ways that you can go about just assuring yourself that you did everything correctly. All right, but at this point, let's go on to the next exercise. This one is inspired by several of the exercises in your homework assignment, exercises which tend to frustrate students year after year. I do hope that you'll give it a sincere attempt on your own first, but obviously this video may provide you some clues if you get stuck. So as we look at this expression here, the radical there provides us with a hint that a good choice for our u function is going to be that expression underneath the radical, x minus 2. So clearly when it comes time to substitute, this will be covered. We'll replace that with u. Now I recommended in the last example, the last exercise, that you tackle the dx next. So this is where we say du over dx, the derivative of u with respect to x. The derivative of this is going to be 1. And this is where we multiply both sides by dx, effectively bringing this dx over here. And whatever constant this is, dividing it over to this side. Obviously in this case, dividing by 1 doesn't really make a difference. But we see that when it comes time to U-substitute, this dx can be replaced by just a du here. So let's take a look at the 2x minus 4 next. If you're really observant, you may notice, hey, look at that. 2x minus 4 is exactly twice this x minus 2. So let's just write for the record, 2u equals 2x minus 4. That's just doubling both sides of this equation. And finally, the last thing that needs to be accounted for is this numerator up here. Let's start by doubling both sides of this equation. That's going to give us 4u equals 4x minus 8. And I'm really interested in 4x minus 9, so let's subtract 1 from each side of that equation, and we'll get 4u minus 1 equals 4x minus 8 minus 1, or minus 9. So now we're set to substitute up there as well. So with everything accounted for, let's do the U-substitution. Up top, 4x minus 9, I'm going to replace with 4u minus 1. So 4u minus 1. 2x minus 4 here, that's going to be replaced by this 2u. So 2u. Plus root x minus 2, that's going to be replaced by this root u. So plus root u. And then finally dx, in this case, is just a swap with du. Okay, so we've got everything in the integral in terms of u now. And this is typically the point where students get stuck. And I don't have any easy answer for how you're supposed to just know what to do next. I could just generally suggest that you dig back in your algebraic memory banks. Think of times before where we've encountered expressions that had some ugly expression down below that had a radical and then a non-radical and the types of things we do, and be willing to just try things and be willing to fail if necessary and have to try something new. In this case, I'd say let's think of how we have rationalized these types of denominators in the past. And something similar came up when we were doing limits. So if you recall back from chapter 1 with limits, we did something that this should remind you of. Can you anticipate what I'm going to write both up here and down below? Something that's going to rationalize the denominator? Well, let's think difference of squares. If this is our a plus b, we're going to write an a minus b. 2u minus square root of u. Again, how are you supposed to know that? Well, no easy answer for that. You just have to be willing to recognize these patterns, these similarities, and try them out. Now, quite often in this situation, I would generally recommend that you FOIL out the top, but you not distribute out the bottom. You may recall me giving that advice. But in this case, our whole purpose for putting this 2u minus root u over 2u minus root u was to rationalize the denominator. So that's an exception. Let's go ahead and FOIL out that bottom, take advantage of our difference of squares pattern, and we're going to get 2u times 2u. That's going to be 4u squared. And then the outer terms, the 2u times minus root u plus root u times 2u, those are going to cancel out. And let's go on to our last term, minus root u times root u. That's going to be minus root u squared, which is just u. Definitely pause if you need to convince yourself of that fact. As far as the top goes, and my general advice of FOILing out the top, I'd say let's just hold on a second. And again, this just takes a little bit of experience and instinct. Let's just hold on a second and just write it without any changes and take a look at what we've got here. If you're really observant, you may notice what our next good move would be. Do you see something up top that cancels out or that divides out with something on the bottom? If you look at the bottom and you factor that bottom, what do you get? Well, you could factor out a u, right, on the bottom. So you factor out a u and you're going to get 4u minus 1. And look at that. That just happens to be the same as that factor up top, 4u minus 1. We are in luck. So here we get to cross out those two factors and let's simplify. So I've got 2u divided by u. That's going to be just 2. Integral, of course. And then I've got minus root u over u. That's going to be minus u to the negative 1/2 du. So let's antiderive that. Antiderivative of 2 with respect to u is going to be 2u. And then as far as the u to the negative 1/2 goes, that's going, if I add 1 to the exponent, I'll get u to the positive 1/2. I'm going to need a 2 out in front to balance it out. Subtraction plus c. So if I bring back my original u definition, we said at the outset that u was equal to x minus 2. We defined it as such. So combine these two or back substitute in for x, and you get 2 times x minus 2 minus 2, x minus 2 to the 1/2 plus c. And I'd be fine with putting a box around this answer. I should point out, of course, that if you wanted to distribute this 2x minus 4. And then if you wanted to write 2 radical x minus 2, that's fine as well. I'm going to keep it as x minus 1/2, x minus 2 to the 1/2 plus c. But I do want to point something out because this can come up. Sometimes what people may do is they may say, I'm going to take that minus 4 and I'm going to move it over here to the end. And then you can make the argument that if c really represents any constant, and you're taking this c constant, which represents any constant, and you're subtracting 4 from it, doesn't that also equal just some arbitrary constant? So one can make an argument that the c and the minus 4 could be swallowed up into just a single c, and we could put a box around that. And that would also be a perfectly acceptable answer. So whether you put a box around this one up here or the bottom one, they're both perfectly fine. Now, as far as checking goes, I'm going to just humbly concede in this case that while we could, I'm sure, we could take our answer and we could derive it and manipulate it algebraically and somehow force ourselves to arrive back at the original integrand. It's possible, but I'm going to admit it's really just not that practical. So again, we'll rely on class time to discuss other means of checking or assuring ourselves that we did everything correct. Now I do have one last little teaser just for your consideration, and it's something that will lead nicely into a topic that's coming up not too far from now. I want to go back up to this process up here, and I wonder if it crossed your mind just what a lucky coincidence it was that we ended up with a factor up top that canceled out or divided out with a factor down below. That was very fortunate in this case, and what would we have done if that didn't happen? What if we didn't have those common factors up top and down below? Well, again, this was a specifically chosen problem such that we knew that would work out. But I'll go ahead and tell you that if up top here, if we had like, instead of minus 9, if that had been a minus 8, or if it had been a minus 10, or just about any other number other than minus 9, guess what? That process would not have worked out the same. And here's the teaser. The process would have involved the natural log function. Craziness, huh?